All right, let's dive in. You're deep in the AI world, maybe an AI researcher, maybe an ML engineer.
Yeah, and you know the feeling. Keeping up with research papers, it's intense.
It really is. Almost a full-time job just reading. So what if we could shortcut that a bit? Get the core insights without spending days on one paper.
That's the plan for today. We're doing a deep dive into a pretty interesting preprint, fresh from 2025.
Okay, what's the paper?
It's titled Breaking the Modality Barrier, Universal Embedding Learning with Multimodal LLMs. Quite a mouthful.
Yeah. Who's behind this one?
It's a team. Tiancheng Gu, Kai-Cheng Yang, Xiong Feng, Xingdun Wang, Yanzhao Zhang, Dingkun Long, Yingge Chen, Weidong Kai, and Jiankang Deng.
Got it. So for anyone needing the quick version, the TLDR right at the start.
Okay, here it is. The paper introduces UniME. It's a new two-stage framework.
UniME, okay.
And it helps multimodal large language models, MLLMs, learn these universal representations. Good for lots of vision language tasks.
How does it work? 2 stages, you said.
Yep. Stage 1 uses textual knowledge distillation, basically learning text embedding smarts from a powerful teacher LLM.
Learning from the master. Makes sense. And stage 2.
Stage 2 is hard negative enhanced instruction tuning. This sharpens its ability to tell similar things apart, discrimination, and follow instructions better.
And does it work?
Seems like it. Experiments show it consistently beats methods like E5V and VLM2VEC, especially on benchmarks like MMEB and retrieval tasks needing compositional understanding.
Compositional, like understanding complex image-text combos.
Exactly. So our mission today is to really unpack UniME, how it works, why it's innovative, the results, and what it means for multimodal AI, especially for you listening.
Perfect. Your AI paper summary, but conversational. So let's set the scene. We need models that get both images and text right. Why is getting these universal embeddings still such a big deal?
Well, think about modern AI apps. Image search based on complex text queries, multimodal RT systems, visual Q&A.
Right. They all rely on understanding both.
Exactly. And under the hood, that means having good multimodal embeddings representing images and text in a shared space where relationships make sense.
And CLIP was kind of the pioneer there, wasn't it?
Absolutely. CLIP was huge, learning image-text connections from web data. But it has its drawbacks.
Like what?
Well, for one, text input is capped at 77 tokens. That's not much for complex descriptions.
Yeah, definitely limited.
And it uses a dual encoder. Image processed here, text processed there. They meet at the end.
Which isn't great for tasks where they need to interact more deeply during processing, like following instructions that mix modes.
Precisely. You lose some of that integrated reasoning. Plus, its language understanding, while good for its time, isn't on par with modern LLMs.
So it struggles with tricky stuff like compositionality. Red car next to blue truck versus blue car next to red truck.
It can, yeah. And sometimes it acts a bit like a bag of words, missing the finer grammatical structure and relationships.
Okay, so CLIP was foundational but had limitations. Then came the LLMs and the multimodal LLMs, MLLMs. Like Quen2VL, Elevate.
Right. And these MLLMs are amazing at complex reasoning, generation, following instructions. They've pushed the boundaries.
But they have their own issues when it comes to creating these embeddings for retrieval, right?
Exactly. They're typically trained using autoregressive next token prediction. Predict the next word.
Standard LLM training.
Yeah. And that objective isn't directly optimized for creating embeddings that are good at comparing similarity between different items, which is what you need for retrieval. Contrastive learning, like CLIP used, is better suited for that specific goal.
So it's a trade-off. MLLMs are great generalists, but maybe not natural-born embedding creators for retrieval tasks.
It's a good way to put it. And people have tried to bridge this gap using MLLMs to create unified embeddings. Models like E5V and VLM2VEC came out of that line of thinking.
But they ran into problems too.
They did. VLM2VEC, for example, really highlighted the false negative problem.
Yes, you mentioned this. Explain that again.
So when you're training with contrastive loss, you have your query, your positive match, and a bunch of negatives. But sometimes a negative sample in your batch is actually semantically related to your query, maybe even a valid match.
Right, it shouldn't be negative.
Exactly. But the standard loss function, InfoNC, treats it as purely negative. It penalizes the model for seeing similarity, which messes up the learning process. It confuses the model about what makes things truly distinct.
Okay, that makes sense. It muddies the waters. So CLIP had limits, MLLMs have a training objective mismatch for embeddings, and previous MLLM embedding methods hit issues like false negatives.
That's the landscape. And that's where UniME steps in with its two-stage approach.
Stage 1. textual discriminative knowledge distillation. Let's break that down.
Okay, the main idea here is to really boost the language understanding part of the MLLM, specifically for creating good embeddings. Remember the autoregressive training limitation.
Yeah, predicting the next token isn't ideal for comparative embeddings.
Right. So UniME leverages a powerful pre-trained text embedding model as a teacher. They used Embed V2.
Embed V2, what's special about it?
It's a strong text embedding model trained on diverse data. Crucially, during its contrastive training, it didn't use the causal attention mask that standard LLMs use for generation.
So it could look forwards and backwards in the text when learning embeddings, giving it richer context.
Exactly. Better for learning discriminative text representations. So in UniME's first stage, they take their student MLLM, freeze the vision parts, and just focus on the LLM component.
Okay, just the language brain.
They feed it text using a specific prompt. Summarize the above sentences in one word. N.
Why that prompt?
It forces the model to condense the meaning into the embedding associated with the very last token, a compact, information-rich representation.
Clever. Get the essence into one vector.
Precisely. They get this summary embedding from the student. Then they get the same kind of embedding from the teacher model, Embed V2, for the same text.
Okay, student embedding, teacher embedding. Now what?
Now, they align them, but not by making the vectors identical. They use Kullback-Leibler divergence, KL divergence.
KL divergence. Measuring the difference between probability distributions.
Exactly. It measures how different the relationships between embeddings are in the teacher's space versus the student space. They want the student to learn the same relative similarities and differences between texts that the teacher knows.
So it's learning the teacher's judgment about text similarity, not just copying homework.
That's a great analogy. It's about transferring that discriminative knowledge. The formula involves comparing the softmax probabilities of similarity scores, using a temperature parameter to smooth things out.
And this works better than just training the student contrastively from scratch.
They argue it's more efficient and leads to better downstream performance. It focuses the learning signal effectively.
Okay, so after stage 1, the LLM part is better at text embeddings. How does the model handle inference, especially multimodal inputs?
Good question. Remember, the vision encoder and the projection layer were frozen during stage 1. For inference, they unfreeze those.
Bring the eyes back online.
Exactly. For text-only input, it uses a standard text prompt. For image-only, a standard image prompt. For inputs with both images and text.
How do they combine?
They process each part using its specific prompt, get the embeddings, and then just do an element-wise sum. Simple but effective.
Got it. Stage 1, beef up the text embedding skill via distillation. Now, stage 2, hard negative enhanced instruction tuning. Why is this needed?
So stage 1 improves text understanding, but the model might still be a bit, let's say, visually naive in terms of fine-grained distinctions needed for multimodal embedding tasks. The image-text alignment might not be perfect yet.
Even though the base MLLM was pre-trained on images and text.
Yeah, the distillation focused heavily on text, plus that summarize in one word prompt isn't ideal for complex instructions you might see in retrieval.
Right, you might want to ask, find images of X doing Y near Z.
Exactly. So stage 2 aims to improve the multimodal discriminative ability, strengthen that image-text alignment, and make the model better at following diverse instructions.
And this involves hard negatives. Let's revisit the false negative problem first. How does UniME handle that contamination?
They implement an explicit filtering step. Before calculating the loss in stage 2, they look at all the negative samples for a given query.
Okay.
Let's calculate a threshold. It's the cosine similarity between the query and the positive sample, plus a small margin, beta.
So anything almost as similar to the query as the actual positive
gets flagged. If a negative sample similarity to the query is above this threshold, they assume it might be a false negative and exclude it from the loss calculation for that step.
Trying to clean up the training signal, data is the tuning knob for how strict they are.
Exactly. It's a hyperparameter. They show in the paper how tuning beta matters. Too aggressive, you might filter out hard negatives. Too lenient, you leave false negatives in.
Makes sense. So after filtering potential false negatives, they focus on hard negatives. Why are these so important?
Because they provide the most useful learning signal. Easy negatives are, well, easy. The model already knows they're different.
No point telling the model a cat isn't a car, it already knows that.
Right, but telling it this specific cat photo isn't the same as that other specific cat photo described by the text query. That requires fine-grained understanding. Hard negatives are those samples that are semantically close to the positive but ultimately incorrect.
They force the model to learn the subtle differences.
Precisely. UniME leverages its stage 1 ability to identify these. Within a batch, for a given query, it looks at all the remaining negatives after filtering.
And picks the toughest ones.
It calculates the similarity between the query and these negatives, ranks them, and selects the top k most similar ones. These are the hard negatives used in the loss.
K is another hyperparameter, the number of hard negatives.
Yes, and if they can't find k, they just duplicate the ones they did find to keep the batch math consistent.
Okay, so filter false negatives, then specifically sample the hardest true negatives. What's the loss function now?
Still into the info NEEC, the noise contrastive estimation loss. But now, the contrast is sharpened. It's calculated between the query, the single positive, and this curated set of A hard negatives.
Pushing the positive closer to the query and specifically pushing these hard negatives further away.
You got it. Concentrating the learning pressure where it matters most for discrimination.
Okay, let's talk training details. The nuts and bolts. Stage 1 sounded efficient.
It did. They used QLARAHAD, quantized low-rank adaptation. It lets you fine-tune large models very efficiently.
Only tuning a small fraction of the parameters.
Yeah, less than 5% in this case, just for the LLM part. And the training times were pretty quick. About an hour for Phi 3.5V, 2 hours for LLVA 1.6 on an 8x A100 GPU setup.
Wow, that's fast for models of this scale. What about stage 2? That sounds more intensive.
It was. Stage 2 fine-tunes all parameters, still using QLRA for efficiency, but it needs larger batch sizes for effective contrastive learning, which bumps up memory requirements.
How did they manage the memory?
They use grad cache, a gradient caching technique. It helps simulate larger batches without needing all the memory up front. They used an effective batch size of 1024.
Okay.
And they set K, the number of hard negatives, to 8 in beta, the false negative threshold to 0.1 based on experiments. Learning rates was smaller too.
And the training time for stage 2?
Considerably longer, about 26 hours for Phi 3.5V, 37 hours for LLVA 1.6 on the same 8 GPUs. So stage 2 is where the heavy lifting for multimodal refinement happens.
Right, makes sense. Significant computation, but hopefully for a significant payoff. Let's talk results. Did UniME deliver?
The results look pretty strong. On the MMEB benchmark for multimodal retrieval, UniME consistently outperformed E5V.
By how much?
Around a 4% average improvement across both base models they tested, Phi 3.5V and LLVA 1.6. They credit stage 1's distillation for a lot of that initial gain.
And stage 2 added more.
Yes. The hard negative tuning pushed the performance further. They even showed a visualization, a similarity matrix where UniME's diagonal is much sharper, meaning corresponding image-text pairs are much more clearly aligned.
Cleaner separation. How did it stack up against VLM2VEC?
Also favorably. Particularly with the Aave backbone, UniME showed a big jump, over 10% improvement compared to VLM2VEC on MMB.
That's substantial. What about other retrieval tasks, like zero-shot image retrieval?
Similar story there. Table 2 shows results on datasets with short captions, long captions, and the compositional sugar crepe benchmark. UniME generally came out on top, especially after stage 2.
And on sugar crepe, the compositional one, that seems like a key test.
It really is. And UniME did well there, showing significant gains over baselines and tasks involving relation changes, object swaps, attribute additions, things that require precise understanding.
Better than even much larger models sometimes.
They noted it was competitive with, or sometimes better, than the 8 billion parameter EVA cliplip in certain sugar creep aspects, highlighting UniME's effectiveness despite potentially using smaller base models.
So it really seems to nail that compositional understanding and fine-grained discrimination.
That's the takeaway.
Yeah.
The performance, especially on sugar crepe, suggests it's learning to handle those subtle but crucial semantic differences effectively.
Let's dig into their analysis a bit. They looked closely at the hard negatives, right? What did that show?
Yeah, figure 5 is interesting. They plotted training loss and gradient norms for easy, random, and hard negatives.
Hazy negatives.
Loss drops fast, gradients vanish. The model learns nothing new. Random negatives, slower loss drop, but hard negatives. The loss stays high for much longer, and the gradients are orders of magnitude larger.
Meaning the model is constantly learning and adjusting significantly from those hard examples.
Exactly. It confirms that focusing on hard negatives forces the model to keep refining its understanding of tricky distinctions.
They also did ablation studies, testing the stages separately.
They did. Table 3 shows the step-by-step improvements. Stage 1 alone gave a big boost over the baseline. Stage 2 alone also gave a big boost, sometimes even more than Stage 1, on certain metrics like MMEB, likely due to better instruction following.
But both together was best.
By far. Integrating both stages sequentially yielded the optimal performance across all tasks, showing they really are complementary. Stage 1 builds the foundation, Stage 2 refines it.
And they tested the hyperparameters too, like beta, the filtering threshold.
Yep. Table 4 shows that too low a beta, negative 0.1, you filter too much, potentially removing useful hard negatives, performance drops. Too high, 0.3, you leave in too many false negatives, performance drops slightly. Beta equals 0.1 seem to be the sweet spot.
Finding that balance. What about K, the number of hard negatives?
Similar trade-off, shown in Table 5. Increasing K from 4 to 8 improved things, likely by adding more diverse challenges. But going beyond K8 started to hurt performance slightly, suggesting they might be adding back too many easier negatives, diluting the focus. So K8 was their optimal choice.
Okay, careful tuning matters. They also visualized the model's outputs. What did that reveal?
Right, figures 6 and 7. They fed images to the model and used that prompt, summary above image in one word, and look at the top predicted words.
Before and after training.
Exactly. Before training, predictions were abstract, like pastoral. After Stage 1, text distillation, they became concrete, like cow or house, but often very focused on one concept, like farm, repeated.
More grounded, but maybe too narrow.
Kinda, but after Stage 2, hard negative tuning, the predictions became much richer. The probability spread more evenly across several relevant words like cow, grass, field, farm.
So a more nuanced and distributed understanding of the image content.
Precisely. It suggests the final embeddings capture more semantic facets and have better discriminative power, able to activate multiple related concepts appropriately.
Okay, bringing this all home, what are the main takeaways for our listeners from this UniME deep dive?
I think the big one is that UniME offers a really promising path towards universal multimodal embeddings. The two-stage approach is clever.
Combining that focused text knowledge distillation with the targeted hard negative tuning.
Exactly. It tackles known limitations, the auto-regressive objective for embeddings, false negatives, compositional weakness, and the results show significant gains, especially in discrimination and understanding complex relationships.
And what does this mean for the wider field? What are the implications?
Well, a unified framework like this that handles diverse tasks well could really boost applications. Think better cross-modal search, more capable multimodal RG, smarter visual Q&A.
Yeah, the downstream impact could be huge.
And the techniques themselves, the specific distillation strategy, the false negative filtering, the hard negative sampling, these offer practical insights for anyone training multimodal models. It's pushing the state-of-the-art forward.
Definitely feels like a solid contribution. So, final thoughts for our audience to chew on. Where could this go next?
That's a great question to end on. For you listening, consider. UniME focuses on vision and language. How could you adapt this two-stage idea, this distillation and hard negative focus, for other modalities? Audio, video, maybe even sensor data or 3D representations.
Extending the universal part even further.
Right. Or could these training strategies benefit different model architectures? Are there ways to make Stage 2 more computationally efficient while retaining the benefits? UniME provides a strong foundation, but it also opens up many exciting questions for future research on the path to truly general and intelligent AI.